Today we will discuss a little bit of statistical mechanics, which may be useful in the solid state physics for the upcoming days to come. As this course of the statistical mechanics is not been encountered in the CBCS till now, so I am discussing a little bit about statistical mechanics. First, we will introduce the microscopic states and averages, and related to magnetic states, angular momentum, and paramagnetism. We all know that different materials respond differently when a magnetic field is applied to them. The simplest response is that as a result of the application of the field, a magnetic moment is induced, which vanishes with the vanishing of the field. If in addition, the induced moment is directed along the field, the response is called paramagnetic. The magnetic moment or the magnetization may also be directed opposite to the field. In this case, the material is called diamagnetic. For this special kind of behavior, and there is a large diversity of other behaviors, but here we will mention only the ferromagnet. Ferro means iron, a substance which at moderate temperature retain its magnetization even after the removal of the magnetic field externally applied. So before going on to the thermodynamic discussion of paramagnetism, we recall that the source of the magnetization that appears in materials is microscopic, and each atom or ion possesses an intrinsic magnetic dipole moment. Actually, this intrinsic dipole moment originates from the electrons of the atom or ion, as shown in this figure. An electron revolving around the nucleus at radius r and velocity v behaves as a circular current of loop pi r square area, and the current is EV divided by 2 pi r. The magnetic moment of the loop is mu is equals to 1 upon 2c 1 upon 2c times EVR, where this equation can be written in the form mu is equals to EL divided by twice MC, or in its vector version mu is equals to minus 2 E by twice MC times L, where m is the mass of the electron and small l is its angular momentum, right? So however, despite the oversimplified assumptions upon which it is based, this connection between the magnetic moment and the mechanical quantities related to the motion of the electron is of general validity. This equation also holds for non-circular orbits and remains valid even within the framework of the quantum mechanics, which is the appropriate theoretical framework for the discussion of the electrons in atoms. In quantum theory, the angular momentum of the electron, or in fact of any other particles, is quantized and can take on values which are integer multiples of the fundamental quantum of angular momentum h cut, that is h upon 2 pi, and the value of Planck's constant is 6.6 into 10 to the power minus 27 R second, or minus 34 joule second. So it is therefore convenient to define dimensionless vector capital L, which measures the angular momentum in units of h cut, like L is equals to small l by h cut, where small l and capital L both called the angular momentum. We will leave no room for confusion between the two of them. The capital L, which is the dimensionless vector of angular momentum in units of h cut, and small l and capital L both are called angular momentum. Now, since the angular momentum, the electron is quantized, the magnetic moment related to it is also quantized. and the fundamental quantum of magnetic moment of the electron is called the Bohr Magneto, so called. The value of the Bohr Magneton mu b is equals to E h cut divided by twice mc is equals to 9.273 into 10 to the power minus 21 arc per Gauss, so that we can write mu is equals to minus mu b times the L, that is the angular momentum. Now look back of the thermodynamics of the magnetic variables, where we have come across that uh, since the dipole prefers to align itself along the direction of the field, it is clear that it has a potential energy that depends on the angle between its direction and the direction of the field, or E magnet is equals to minus mu dot B from the previous this type of curves, where we have shown that view of the magnetic moment of the loop and B uh, if m is the magnetization density or magnetization per unit volume, the relation between the induced fields and the polarization density is B is equals to 4 pi m. And consider, for example, a single dipole moment in a medium of many other dipoles. It will feel the external field H and also the additional field 4 pi m originating from the neighboring dipoles. The sum of these two effects in the magnetic induction B and the relationship between is B is equals to H plus 4 pi m. And the similar relationship can formulated for the electric field also. And furthermore, the first law of thermodynamics becomes, in case of magnetic variables, where dE, the internal energy is nothing but the difference between the delta Q minus delta W. D is the increase in the energy of the system, delta Q is the heat transfer to the system, and delta W is the work done by the system, where it turns out to be in terms of E, we express the entropy change of the form TdS is equals to dE minus HTM, which is more corresponding to the equation of gaseous, in that both differences are of extensive quantities, except for the sign difference. Instead of PdV, here we have applied minus HTM. Now quickly go on that mu is equals to minus mu b times capital L. That means because in addition to the orbital angular momentum small l, the electron also possesses an internal angular momentum or spin, that is S. Like all angular momenta, also the spin assumes only discrete values, but in contrast to the orbital angular momentum, which can take on integral multiples of h cut, the spin can take on half integral values. The spin of the electron can take on the values plus minus half h cut only. So on the basis of the equation mu is equals to minus E by twice mc times L, we could expect the spin itself to create an additional magnetic moment of half mu b, but this is not so. A magnitude twice as large is found experimentally. Hence, the relationship between the magnetic moment and the spin of the electron is nothing but mu is equals to minus E upon m times small s, that is minus twice mu b times capital S. Where again we have defined a dimensional spin, capital S is equals to small s divided by h cut. The reason for the fact of two discrepancy with the expected value of the electron's magnetic moment is explained by taking into account relativistic effects of the quantum treatment of the electrons as done by Dirac. And actually the true value is slightly larger than 2, and the fact can be explained within the framework of the quantum electrodynamics, QED. So the total magnetic moment of a single electron is thus the sum of mu is equals to minus mu b times L and mu is equals to minus twice mu b times S. So one is this and another is this, right? So the magnetic moment of the whole atom or ion, which is in fact our main interest, is the sum of the contributions of all its electrons. The electrons in the atom are arranged in shells so that each electron in every shell has a specific angular momentum. The total angular momentum of electrons is a full shell or subshell is zero. If one electron is added to or removed from a full shell, the ion remains with an angular momentum equal in size to the angular momentum of the additional or missing electron. Since a charged particle possessing angular momentum has a magnetic moment, we can assign the ion that magnetic moment. So the magnetic moment of the ion is proportional to its total dimensionless angular momentum. J is equals to summation upon I Li times Li, and with addition to the spin angular momentum Si. And moreover, it is possible to show that in an external magnetic field, the ion increases its energy by an amount which is proportional to this total angular momentum J by delta E is equals to G mu B J dot H, where G is the numerical factor of order 1 which is determined by the structure of the atom. Normally it is called gyromagnetic factor, and it actually describes the ratio between the magnetic moment of the ion and its total angular momentum. For a free electron, we obtain G is equals to 2, and as an example we consider doubly ionized copper Cu++. In the external shell, the fourth shell, Cu, contains a single electron. The double ionization removes this last electron as well as one from the full highest subshell of the third shell, that is 3D. The ion has a single hole in the 3D shell with angular momentum 5 by 2 h cut. There are different kinds of paramagnets. Here we discuss a type for which the ions possessing angular momenta are set in fixed positions in a crystal. For example, in ionic crystals of copper salts, manganese or gadolinium, the ions Cu double plus, Mn double plus and Gd double plus give rise to the paramagnetism of the salt. If there are many non-magnetic atoms in the salt per magnetic ion, then it is reasonably to assume that due to the large separation of the magnetic ions, they do not affect one another. This is the case, for example, in copper potassium sulfate, that is CuSO4, K2SO4, 6H2. Then we gradually discuss the microscopic states or observables. The simplest case that we begin with is a paramagnet in which n magnetic ions have spin half. This means that any projection or component of capital S may take on values plus minus half only, right? So if a field capital H is applied to a single moment mu I, the energy is given by epsilon I is equals to minus mu I dot H. However, in our case, the magnetic moment can have only two projections along the field, either mu b or minus mu b, so that we can write epsilon I is equals to minus mu b H sigma I, where sigma I takes the value is a variable that has two possible values, which is plus 1 or minus 1. Sigma describes the projection of the spin along the direction of the field. In the case of spin half, its projection along the field is h cut sigma divided by 2, where sigma is equals to plus minus 1. Since we are assuming that the magnetic moments are far from one another, which means that there is no interaction between the magnetic ions, we can write the energy of a configuration or a microscopic state of the system of moments in the form E is a function of sigma 1 to sigma n is equals to minus mu b h summation upon I is equals to 1 to n sigma I, And by the term configuration or microscopic state, we mean a state in which all the degrees of freedom of the system are specified, right? So in the present case of the system has capital N degrees of freedom corresponding to capital N magnetic moments, which we denote by sigma I. Each degree of freedom can assume one of two possible values. Sigma I is equals to plus minus 1 because we choose ions with spin half. If each sigma I is assigned a value, the specific configuration or a specific microscopic state is determined. For instance, the configuration sigma I is equals to plus 1 for every I is the state in which all the magnetic moments point along the field, while sigma I is equals to minus 1 for every I is the state in which all the magnetic moments are opposite to the field. So in this figure shown depicts a lattice on which there are spherical atoms, right? These are the spherical atoms, black and white, which have zero magnetic moments. So there are also elongated atoms, this arrow, with arrowheads representing their magnetic moments. Their serial number is I, and the projection of their magnetic moment along the z-axis, which is chosen, z-axis as the external magnetic field direction, is plus minus mu b. So there is no interaction between them. This is our model system. This system has 2 to the power n microscopic states, right? 2 to the power n microscopic states. Each of them is characterized by n numbers, that is sigma 1 2 dot 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 sigma n, which determine the projection of each spin. In each microscopic state, the properties of the system are completely defined. With each microscopic state, one can associate observables like A, sigma 1, sigma 2, like sigma n, which are numbers associated with the particular state. For instance, the total magnetic moment along the z-axis is an observable given by some magnetic moment is a function of sigma 1 to sigma n is equals to mu b summation upon I is equals to 1 to n sigma I is the total energy given by the last one. E is equals to minus mu b h summation upon sigma I, right? So the magnetic moment of a subsystem with Na of the n magnetic moments is an observable of the full system, right? Ma sigma 1 to sigma n is equals to mu b summation I equals to 1 to Na times sigma I. Despite the fact that it depends only on part of the variables, so is the energy of the subsystem Ea is equals to minus Hma, right? And the value of a particular spin sigma I is also an observable, etc. So with a little extra effort, it is possible to generalize the present model of the case in which the ions have an angular momentum J is greater than half, where J is the sum of the orbital angular momentum and the spin, right? So in this case, the possible values of the projection of the angular momentum along H are Jz is equals to minus J plus 1 minus J plus 2 to J. So there are 2J plus 1 possible projections, and the energy levels of each an ion are given again by multiplying mu b JZH by the gyromagnetic factor. So all the expressions that we have written in this section still hold, with the presumption that every degree of freedom will now have 2J plus 1 states instead of just 2. So consequently, there are now 2J plus 1 to the power n microscopic states.